A 0.15 kilogram mass is attached to a horizontal spring, simple harmonic motion, and we have a plot of the kinetic energy versus position. The total energy of the oscillating system is 3.4 millijoules. Draw the graph of total energy, draw the graph of elastic potential energy. What is the maximum displacement of the oscillating mass, and what is the spring constant? What is the potential energy at the position of 0.6 centimeters? It's going to be somewhere around here. What is the kinetic energy at that position? Find the location of the oscillating mass when its potential energy is 2 millijoules. And what is the period of oscillations? Draw the graph of total energy. Well, the total energy is a constant. It's 3.4 millijoules. There's no friction involved here. It wasn't mentioned. And we only extend the graph to the farthest that the mass is displaced, which is going to be 1.5 centimeters to negative 1.5 centimeters. If we extend it like here, this has no meaning, so you're not supposed to do that. Draw the graph of elastic potential energy as a function of position. Well, let's see. We know at the endpoints you have zero kinetic energy, because the mass momentarily stops before reversing direction, so you'll have a maximum EPE, which will equal the total energy. In the middle, you have maximum kinetic energy, so you'll have a zero elastic potential energy. And then you just know, hopefully from working the problems, that it's a curve that connects up those 3 points, so that's your elastic potential energy. And as mentioned earlier, you can pick any points, let's say at 1 centimeter, pick where the KE is and where the EPE is and add them together, and they're going to add up to form a straight line. That's pretty cool. Two curves added together, you get a nice straight line. What is the maximum displacement of the oscillating mass? That's when all the energy is in the form of EPE and you have no energy in the form of KE. That's where the mass momentarily stops before reversing direction. That's going to happen at 1.5 centimeters and negative 1.5 centimeters. So you could give either answer or both. A lot of times people just give this, and that's just fine. What is the spring constant? We're going to use the EPE equation, and we want to pick a point where at least one of the values is right on one of the lines. And fortunately, we have here at 1.5 centimeters, the EPE is 3.4. And you know what? You didn't even have to read it at the chart, because we knew, off the graph, because we knew that the total energy is 3.4. So X is 1.5 centimeters, EPE is 3.4 millijoules. And of course, you could have picked any other point on these two graphs, but it'd be a little harder to see. So we isolate this equation for K by multiplying both sides by 2 over X squared. We then put in our values, and of course, convert millijoules to joules and centimeters to meters. Centimeters to meters, you move the decimal point 2 to the left. Millijoules to joules, move the decimal point 3 to the left. Carry out the math, and you get 30.2 newtons per meter. What is the potential energy at the position 0.6 centimeters? One way to do it, just use the graph. Go right up to where the curve for EPE is and cut over, and that gives you about 0.55 millijoules. Another way is to use this equation, the EPE equation, where we calculated K, X were given, right, because that's the problem, and notice how 0.6 centimeters becomes 0.006 meters when we move the decimal 2 to the left, and we get the elastic potential energy as 5.44 times 10 to the minus 4th joules. What is the kinetic energy at the position of 0.6 centimeters? We've already found at 0.6 centimeters the EPE was 0.544 millijoules. The total energy is this, 3.4. So how could we find the kinetic? Just subtract them, right? Because the sum of EPE and kinetic energy has to equal the total energy. So here's that. E total is EPE plus KE. KE is E total minus EPE. E total, EPE, and we get 2.85 millijoules. The other thing you can do is just try and read it off the graph. So you go 0.6 up here, right? Hit the KE curve, go over here, and you can say that's about 2.85 millijoules. So we're good. Find the location of the oscillating mass when its potential energy is 2 millijoules. So this time you can go right to the graph. Here's 2 millijoules. Go till you hit the EPE curve, come on down, and it's about 1.15 centimeters. Or use the equation. EPE is 1/2 kx squared. Multiply both sides by 2 over k. All right, that'll cancel this, so you're just left with x squared. And you have a 2 over k in front of the EPE. Then take the square root, right? Because we don't want x squared, we want x. Once again, we go from millijoules to joules by moving the decimal 3 places. So 2 millijoules is 0.002 joules. Here's our value of k that we found, and we get 1.15 centimeters. And can't underestimate doing this, or overestimate, not sure, but make sure you convert your units. And finally, find the period of oscillations, and we just use our 2 pi times the square root of m over k equation. We have the mass in kilograms, we have k that we found, divide them, make sure you take the square root, and we get a period of 0.443 seconds.